On February 14th, a massive research vessel named the Chikyu pulled quietly into Shimizu port in Shizuoka. It wasn't carrying standard cargo or the day's catch. Instead, deep within its hold were samples of dark, heavy mud pulled from a place where sunlight hasn't touched the earth for millennia, the seabed over 5,500 meters below the Pacific. To the scientists on board, this wasn't just silt, it was a technological gold mine. Specifically, it was rare earth mud rich in elements like dysprosium and gadolinium, the invisible, essential components that power everything from the motors in your electric vehicle to the control systems of nuclear reactors. For decades, the global narrative has been fixed. Japan is a resource-poor nation, a manufacturing giant forever at the mercy of foreign suppliers, particularly China, which currently provides over 60% of its rare earth needs. This successful extraction felt like a long-awaited hitback. With an estimated 16 million tons of these materials sitting in their own backyard, the mood among the project leaders was one of quiet, giddy triumph. They had achieved a world first, proving that they could reach into the abyss and pull out the very foundation of 21st century industry. On paper, it looks like the ultimate move for economic independence. But as the ship docked and the initial excitement settled, a cold, sobering reality began to emerge. It's one thing to pull a few samples from the deep. It's another entirely to build an industry where none exists. One researcher from the U.S. Ames National Laboratory put it bluntly, there is no precedent for this. Japan currently has almost zero infrastructure to refine this mud. The material is wet, the impurities are unknown, and the logistics of transporting thousands of tons of seabed from 5 kilometers down are staggering. Despite having already poured 40 billion yen into the project, the government is essentially staring at a treasure chest located at the bottom of a crushing abyss without a key to open it. It raises a haunting question that the data doesn't yet answer. Is this a masterstroke of national security that will finally break a superpower's monopoly? Or is it a multi-billion-dollar gamble on a smart mine that may never actually turn a profit? To understand if Japan has truly struck gold, or just found a very expensive way to dig a hole, we have to look at what happens the moment that mud leaves the water. So that opening, it really sets the stage, doesn't it? It's basically a high-stakes poker game, but, it's being played 5 kilometers under the surface of the ocean.
Yeah. And the documents we have in front of us, it's not a simple story. You've got these incredibly dense technical schematics from the Chikme expedition itself.
Right next to intelligence reports on, naval movements in the Pacific. It's wild.
And then economic white papers analyzing supply chains. It's this perfect storm of geology, high-stakes engineering, and raw geopolitics.
I think it's rare to see a single project that touches on so many different kinds of risk all at once.
Absolutely. You've got the extreme physical risk of just operating in the deep ocean, which is, it's basically outer space, but with more pressure.
Yeah.
Then there's the economic risk of a totally unproven market. And layered on top of all of that is the geopolitical risk of directly challenging, the hegemonic supplier of these materials.
We're basically watching a country try to engineer its own luck, to rewrite its own geological destiny in real time.
Geological destiny.
Let's start there. Because usually when we talk about a country's natural resources, it's about, the luck of the draw. You either have oil under your deserts or you don't.
Right. You have iron ore in your mountains or it's not there.
Exactly. But this whole situation with Japan and this spot in the ocean, Minamitorishima, it feels different. It feels less like they stumbled upon a resource and more like they're trying to will one into existence through sheer force of technology and, government spending.
That's a really sharp distinction, and it's the right one. To get your head around why they're doing this, you have to try and get into the headspace of the people in Tokyo who are signing the checks.
Okay.
So let's build a little persona here. He's a veteran strategist, maybe at the Ministry of Economy, Trade, and Industry.
So he's seen it all?
He spent the last, say, 15, 20 years of his career just watching the price tickers for rare earth elements bounce around, watching the global flow of these critical minerals.
And for a guy like Sato in that position in Japan, that has not been a relaxing job.
It's been the opposite of relaxing. It's been a source of constant low-grade anxiety that occasionally spikes into sheer terror. If you are Sato, your entire professional worldview is shaped by a single trauma.
The shock of 2010.
The shock of 2010.
Yeah.
That's the moment everything changed for him, for Japan. Before 2010, rare earths were. They were just another line item on a spreadsheet, a commodity. You bought them on the market, you used them to build incredible things.
And China was a reliable supplier?
They were the supplier.
Yeah.
But after that incident, the collision between a Chinese fishing trawler and a Japanese Coast Guard ship near the Senkaku Islands, Everything froze.
The supply lines from the continent they didn't officially get cut, but they tightened up.
They tightened to the point of strangulation. And the silence from the suppliers was, as one report put it, chilling.
It was a message.
A very clear message that the supply chain wasn't neutral. It was a lever. It was political. And in that moment, Sato and everyone like him in Tokyo had this horrifying realization. The high-tech heart of Japan, its world-beating auto industry, its consumer electronics sector, its advanced defense capabilities, all of it was essentially on life support. And the plug was in Beijing. They were building some of the most advanced machines in the world, but the vitamins for those machines, the dysprosium and terbium, were controlled by a foreign power that had just shown it was willing to turn off the tap.
So that's the background anxiety, the trauma that's been simmering for over a decade.
Exactly. So fast forward to February 14th. When that ship, the Chikyu, pulls into Shimizu port with those samples of mud, Sato isn't just looking at a scientific breakthrough on the evening news.
He's exhaling.
He is taking a deep, deep breath that he's been holding since 2010.
And it's all because of where that mud came from.
It's everything. He's looking at the coordinates on a map for Minamitorishima. I mean, you have to look it up. It is a tiny, remote, uninhabited speck in the middle of the Pacific Ocean. It's about 1,900 kilometers southeast of Tokyo.
But the crucial part is, it's Japanese soil. It is unambiguously within Japan's exclusive economic zone, their EEZ.
Yes. So when Sato looks at that heavy, dark mud, the sample rich in dysprosium and gadolinium, he doesn't just see minerals with weird names. He sees the physical components of national sovereignty. He sees independence.
It's this visceral survival instinct of an island nation that's always been resource poor, finally trying to find a way to stand on its own 2 feet.
But he also knows this path, this resource independence.
Yeah.
It doesn't happen in a vacuum. It creates new problems, new tensions in the Indo-Pacific.
Okay, this is where I need to push back a little, because we can talk about sovereignty and these very powerful emotional motivators. Business, it's about numbers on a page.
Right.
And if this project is just a government vanity project to make people like Sato feel more secure, it's going to be a black hole for money forever. I'm looking at some of this analysis here, this theory of state-built option creation. That sounds like very academic jargon for we're going to subsidize something that the private market absolutely hates.
It is certainly a form of subsidy, but framing it as option creation is important. This thinking comes from research by Peter Bell, and the argument is that you can't evaluate the Minamitorishima project as if it were a normal mine.
So,
a traditional mine is an asset. You find it, you dig it up, you sell what you find, and you try to make an immediate profit. This project is something different. It's what he calls an uncertainty reduction sequence.
for us, what uncertainty are they trying to reduce?
Think about all the reasons a private company would run screaming from this. First, you have what economists call capital specificity. The multi-billion-dollar ship, the 6-kilometer riser pipe, the onboard processing plant.
You can't use that for anything else. If the mine fails, that's all just scrap metal.
Exactly. That's a huge risk. Second, you have extreme technical risk. Nobody has ever mined mud from 6,000 meters deep at a commercial scale before. Nobody knows if it can be done reliably for years on end.
Yeah. And the third one has to be market risk.
The market risk is the killer. China can, if it chooses to, flood the market with cheap rare earths tomorrow and drive the price down so far that your incredibly expensive deep-sea operation is instantly bankrupt.
So you got specific capital, technical risk, market risk. No private CEO, not at Toyota, not at Mitsubishi, is going to take that package to their shareholders. They'd be fired.
They'd be laughed out of the boardroom. So the private sector looks at this and says, no thank you. Call us when it actually works, and all the risk is gone.
So private companies can't afford to buy the information they would need to see if this is even viable?
They can't. So the Japanese state has to step in. The government isn't playing the same game. They're not looking for a profit in the next quarter. They are purchasing information. They're paying for learning. Their entire goal right now is just to prove that the end-to-end production pathway, from lifting the mud to handling it on the ship to refining it on shore, is physically possible.
So they're not buying minerals yet. They're buying the option to have a domestic supply chain in the future.
Exactly. Think of it like a strategic petroleum reserve. But instead of just buying a bunch of foreign oil and sticking it in a salt dome, they are building the capacity to produce their own. They're building a platform.
So it's about leverage.
It's all about leverage. If they can demonstrate that this platform works, even at a small scale, they have effectively created a ceiling on how much geopolitical pressure can be applied to them. It creates what they call a boundary event.
Meaning if China threatens to cut supply again,
Japan can walk into the negotiating room and say, fine, we will activate the Minamitorishima option. It might be more expensive, but we won't be brought to our knees.
it's a very, very expensive insurance policy that you hope you never have to fully cash in, but just having it changes the entire negotiation. Yeah.
And you can see how this is a different model from what we see elsewhere. You have the Chinese model, you know, the giant Ban-Obo mining complex, which is just massive state consolidation and strict quotas. It's a blunt instrument. Then you've got what you could call the Western model, like the Lynas Rare Earths facility in Australia and in Malaysia. That's more of a hybrid. It's a private company, but it's heavily backed by government loans and strategic partnerships.
So Japan is carving out a third way here.
They're trying to. It's direct state-led platform governance. The government is doing the really dirty, extensive R&D that is just too toxic for the private market to touch.
And the reason they're willing to get their hands dirty is that the China factor, as we're calling it, isn't a theoretical threat. It's getting worse.
It is tightening significantly. Yeah. And the numbers, I mean, the numbers really tell the story. China currently controls something like 68% of global rare earth mining output.
Which is a dominant position, but it's not 100%. It's not a total monopoly on mining.
Correct. The monopoly isn't in the mining. It's in the next step. When you move up the value chain to refining, the complex process of turning that raw ore into usable metals and alloys, China's share jumps to about 90% of global capacity.
And that is the choke point. You can dig this stuff up in Australia or the US or wherever, but if you still have to ship it to China to be processed, you haven't really solved the core problem.
You haven't solved it at all. And for the most critical elements, the heavy rare earths like dysprosium and terbium, which are essential for the high-performance magnets in EVs and missile guidance systems.
The exact elements they're targeting at Minamitorishima.
The very same ones. For those, China's control over refining is effectively 100%. And we've seen recent escalations that have made this an acutely painful reality for Japanese industry.
What kind of escalations?
Well, in April of 2025, Beijing rolled out much stricter export controls on 7 specific types of rare earth, and they cited, the usual national security concern.
Standard procedure.
Right. But then in October 2025, they went a step further. They put in a new requirement that any foreign company had to report the rare earth content in their products if it exceeded just 0.1%.
0.1%. That sounds like a bureaucratic weapon. If you're a Japanese car maker or an electronics company, that level of reporting must be an absolute nightmare.
It's designed to be. It's a dual-use restriction. It gives Chinese regulators the power to halt any shipment at the border to conduct an audit on that 0.1% claim. And we've already seen the impact. We have reports of Japanese automakers having to temporarily halt production lines because of these new administrative delays.
So it's 2010 all over again, but with paperwork instead of an outright embargo.
It revives all those memories. It's a constant reminder to every CEO in Tokyo that their multi-billion-dollar supply chain exists entirely at the pleasure of a strategic rival.
And it's not just happening on paper, is it? There's movement in the water as well.
Yes. In June of 2025, the Chinese aircraft carrier, the Liaoning, along with its strike group, entered Japan's exclusive economic zone, and they conducted drills specifically in the waters near Minamitorishima. There are no coincidences when you're talking about naval maneuvers on that scale. As we said, Minamitorishima is in the middle of nowhere. For a carrier strike group to go all the way out there and operate, that is a very deliberate, very specific signal.
The signal being, we see what you're doing.
We see your little science project out here, and just so you know, we can reach you anytime we want. It instantly transforms what was a commercial or scientific project into a theater of military and naval signaling.
Which I imagine is why the United States has suddenly become very interested in deep-sea mud. I'm looking at reports here on a new U.S.-Japan deep-sea alliance.
The U.S. is watching this with extreme interest. This joint deep-sea mining demonstration that's set to launch in January 2026 is the clearest evidence of that alignment.
What's the U.S. interest here?
The U.S. has the same vulnerability as Japan, just on a different scale. They realize they cannot possibly build enough domestic refining capacity to match China in the short or even medium term. It's too expensive, too slow, and environmentally difficult. So they need what the Pentagon calls a distributed multi-domain supply strategy.
Which is a fancy way of saying they need friends with mines.
They need friends with mines. They need mines in the Australian desert. They need potential mines in the mountains of North America. And now they're realizing they might need mines at the bottom of the ocean. It's about diversity of supply. Anything to break that single point of failure, that monopoly leverage that Beijing currently holds.
But, and this is the pivot we have to make, all the alliances and treaties and geopolitical strategies in the world don't actually lift a single gram of mud from the seabed.
No, physics does. And the ocean floor, as you said, is not a hospitable place for any kind of industrial machinery.
So that brings us to the actual operation, the engineering. I want to shift our perspective now from Sato in his Tokyo office down to the people actually on the deck of the Chikyu. I was reading these logs from a young subsea engineer, and we talk about the deep sea so casually, but I really don't think people can grasp the sheer violence of that environment.
It's an alien world. It's not just deep. We're talking about depths of 5,569 meters. To put that in perspective, that's deeper than the Grand Canyon is deep. The pressure at that depth is over 500 atmospheres. It's a darkness so absolute that the engineer described it as feeling solid.
He also described the drill pipe as a fragile straw. You have this massive high-tech research vessel the size of a building heaving on the surface of the Pacific, and dangling from it is this nearly 6-kilometer-long steel pipe.
That pipe is called the riser, and it is, without a doubt, the single most vulnerable and critical part of the entire system. Well, the steel pipes used in standard offshore oil and gas drilling are typically rated for depths of maybe 1,000, 2,000 meters. Pushing that technology to nearly 6,000 meters introduces structural stresses that are almost impossible to model accurately.
So it's not just holding its own weight.
It's holding its own immense weight, which is hundreds of tons. Then you have to add the drag from deep ocean currents pushing against it, and the constant heaving and swaying motion of the ship on the surface in rough seas. The engineer's logs describe this constant, rhythmic, metallic groaning sound that travels up the pipe. It's the sound of steel stretching at its absolute limit.
And the whole point of this fragile straw isn't just to touch the bottom, it's to suck the bottom up to the surface. And this is where the engineering gets, I think, really clever. The documentation talks about a new technique called pulp lifting.
This is a critical innovation.
Yeah.
This is what makes the whole thing potentially possible. The problem they were facing was friction.
With the mud.
The rare earth mud on the seabed is not like sand. It's very fine-grained, it's sticky, it's cohesive. If you just try to pump that pure mud up a 6-kilometer straw, the friction against the inside walls of the pipe would be enormous. The pumps you would need would have impossible power requirements.
It sounds like trying to suck a really thick milkshake through a very long, very thin straw.
So the engineers on the Chikyu did something completely counterintuitive. They decided to solve the problem by mixing the mud with rocks.
Wait, they're adding solids to the flow? Usually with any kind of pumping system, you want to get rid of solids to prevent clogs and wear.
I know, it sounds crazy, but in this specific case, the solids act like tiny ball bearings. They go out and they harvest these ferromanganese nodules. You've probably seen pictures. They look like dark, lumpy potatoes scattered on the seabed.
Right, and they're rich in other metals like cobalt and nickel.
Exactly. So they have a machine that scoops up these nodules, crushes them into a specific size, and then mixes them with the mud and seawater to create what they call a pulp.
And what does that do to the flow?
By creating this mixture with about a 55% solid volumetric concentration, the crushed nodules break up the cohesion of that sticky mud. They physically reduce the frictional resistance inside the riser pipe. The amazing thing is the slurry actually flows more easily with the rocks in it than it would as pure mud.
So they're basically using one valuable resource, the nodules, as a tool to facilitate the extraction of the other valuable resource, the mud.
It's a combined mining approach. They have a hydraulic cutter that kind of stirs up the mud like a giant egg beater, and a separate hydraulic suction head that gobbles up the nodules. It all gets mixed together at the bottom and then pumped to the surface.
And once it gets to the surface, they have to separate it all out again.
Right. On board the ship, they have a series of hydrocyclone separators. These spin the slurry at high speed, using centrifugal force to separate the heavier mud particles from the water and the lighter nodule fragments.
But getting the stuff onto the ship is really only half the battle. The engineer's log keeps mentioning the state of the material when it arrives on deck. It's not like they're dumping out dry ore.
Not even close. What arrives on deck is a slurry, and it has a water content of somewhere between 300 and 500%. So for every 1 part solid, there are 3 to 5 parts water.
So it's basically a dirty, salty soup.
And you can't just load that onto a bulk transport ship and send it to a port in Japan. It's far too voluminous and way too heavy. You'd go bankrupt just paying for the fuel to transport all that seawater across the Pacific.
Which means the Chikyu can't just be a mining ship. It has to be a floating factory, a processing plant.
And that's what's so complex about it. They have this 4-tank gravity settling system on board. It's a continuous 4-day cycle. They pump the slurry into the first tank, let gravity do its work, pulling the solids down, and then they carefully drain off the water from the top. Then they move the thickened sludge to the next tank and repeat.
And they heat it.
After the gravity settling, they heat the remaining sludge to between 60 and 110 degrees Celsius to drive off even more water. The goal is to get it down to a manageable consistency, like a thick paste, before they offload it.
And this is where we run smack into the big environmental question, because you are separating out enormous volumes of water that came from the absolute bottom of the abyss, and you have to put it somewhere.
You have to put it back in the ocean. There's nowhere else for it to go. And this is what's referred to as the silent ecosystem problem. The operational plan is to discharge this supernatant water at a depth of about 500 meters.
But that water's not the same as the water at 500 liters.
It came from 5,500 meters, so it has a different temperature, a different salinity, different nutrient levels, and crucially, it likely contains very fine sediment plumes, tiny particles of mud that didn't settle out in the tanks.
And we don't really know what lives down there, do we? Not in any detail.
We have very, very little data. The deep seabed is an incredibly stable, low-energy environment. The creatures that live there grow incredibly slowly. A disturbance like a mining operation, which creates these sediment plumes that can settle over a wide area. It could smother entire ecosystems of organisms that we haven't even cataloged yet.
So it's the central paradox of the green transformation. In order to get the green materials, we need to build a sustainable future above the water, the dysprosium for EV motors and wind turbines. We are potentially wrecking one of the last pristine, untouched ecosystems below the water.
It creates this huge zone of environmental ambiguity. The Chikyu trial does include environmental impact assessments. They're monitoring the water column, but establishing proper biological baselines in the deep ocean takes years, sometimes decades.
And the project isn't moving at the speed of biological science.
No, it's moving at the speed of industrial necessity and geopolitical urgency. And those two things are always much, much faster.
So, okay, let's take a step back. We have the geopolitical necessity that's driving this whole project. We have this incredible engineering marvel that's making it physically possible, albeit with some big environmental question marks. But there's a third leg to the stool that we have to talk about, and that's the economics. Because you can have the national will and you can have the technology, but if the math doesn't work, the project eventually dies.
And the economics are, without a doubt, the harshest reality check in this entire story.
So to ground this part of the conversation, I want to introduce our third perspective. We've had Sato, the strategist, and the subsea engineer on the boat. Now let's think about a guy we'll call Tanaka.
Okay.
Tanaka owns a small, specialized factory in Shizuoka. He manufactures high-efficiency magnets for industrial motors. He's the guy at the very, very end of this long, complicated supply chain.
And he's the one who is most exposed to the raw forces of the market.
For Tanaka, national sovereignty is a nice idea he hears on the news, but his day-to-day reality is his ledger book. He has spent his entire career living at the mercy of global price fluctuations that are dictated by boardroom decisions in Beijing.
He has no control.
So he sees the Minamitorishima project on TV, and he feels this mix of hope and deep skepticism. The hope is obvious, a true made-in-Japan supply chain that would finally shield his business from trade wars and embargoes. But the skepticism comes from the fact that he knows business. He knows that digging mud from 5 kilometers under the ocean has to be exponentially more expensive than an open-pit mine in Inner Mongolia.
Tanaka is right to be skeptical. If you look at the base case economic studies for this project, the numbers are just brutal. The early analyses looking at just mining the rare earth mud by itself showed a deeply negative net present value, or NPV.
Meaning, for every dollar you invest in digging it up, you are guaranteed to get less than $1 back in revenue.
In a purely free market, this mine would never, ever open. The operational expenditure, the OPEX, is just a killer. You're talking about the fuel for the ships to go back and forth, the constant high cost of replacing those riser pipes, which are under immense stress.
How long do those pipes even last?
Well, in shallower offshore oil at maybe 1,700 meters, they last 2 to 5 years. At 5,800 meters with the added stress, nobody really knows, but the replacement costs are going to be astronomical. It just crushes the potential profit margins.
So how are they justifying this financially? Is it purely That security premium we talked about earlier, just a straight-up government subsidy for national security?
That is a huge part of it, yes. The government has already poured about 40 billion yen into this project since 2018. And there's another 16.4 billion earmarked in the new budget for what they're calling an ocean security platform. So they are absolutely subsidizing the gap between the cost of this deep sea extraction and the global market price. They're essentially paying Tanaka's security bill for him.
But there has to be an attempt to fix the math, right? To make it at least look viable on paper.
Yes. And that's where the combined mining approach comes back in. Not just as an engineering solution, but as an economic one.
The nodules?
The nodules save the day economically. By harvesting the manganese nodules alongside the mud, they're not just getting a pumping aid, they're getting a whole other stream of revenue from the cobalt, nickel, and copper in those nodules.
Which are all critical battery metals with their own strong markets.
Very strong markets. And the revenue from selling those metals effectively helps to subsidize the much more expensive process of extracting and refining the rare earths. It's the key that shifts the overall project NPV from definitely negative to potentially positive, but only if they can achieve very high levels of efficiency.
But there's a huge bottleneck here that I don't think gets enough attention. Even if the ship works perfectly, and even if the combined mining makes the numbers look a little better, what happens the moment that semi-processed mud gets to the port in Japan?
You've hit on the missing middle. And it is arguably the single biggest risk in this entire multi-billion-dollar gamble. Japan currently has almost zero industrial-scale infrastructure to refine this specific type of deep-sea mud.
Zero. Not just not enough, but zero.
Effectively zero. You have to understand, refining rare earths is not like smelting iron ore. Complex chemical engineering. You're trying to separate 17 different elements that are all chemically almost identical to each other.
And this deep-sea mud presents its own unique challenges, different from terrestrial ores.
Completely different. First, it's still wet even after the onboard processing. Second, it has a very high salt content from the seawater, which is incredibly corrosive to standard refining equipment. And third, it has a totally different mix of impurities, other minerals, biological matter, that land-based ores simply don't have.
So you can't just truck this stuff over to an existing refinery and dump it in the furnace.
Not. You need a brand new, purpose-built facility designed specifically for this feedstock. The proposed method is called SCL, that's smelting and chemical leaching. It's a complex process involving high-temperature smelting to create a glass-like slag, followed by multiple stages of acid leaching to selectively dissolve and separate out the valuable rare earths.
Does an industrial-scale SCL plant actually exist anywhere?
It exists on paper. It exists in small-scale laboratory tests. But building a full-scale SCL plant is a multi-billion-dollar investment in its own right. And this is where you hit the classic chicken and egg problem.
Okay.
No private company is going to spend billions to build that refinery unless they are guaranteed a steady, reliable supply of thousands of tons of this mud every single year.
But the mining operation can't guarantee that supply until they prove that the deep-sea mining works at a commercial scale.
And the mining operation can't be commercially viable if there's no one there to buy and process the mud they bring up.
It's a perfect deadlock. Tanaka, back in his magnet factory, he can't buy the raw mud from the ship. He needs the finished 99.9% pure dysprosium metal. If that middle part of the chain isn't built, then all that mud they bring up is just expensive, slightly toxic waste sitting on a dock.
They are trying to find clever ways around it, like proposing to reuse the waste products.
From the refinery.
Yeah, the plan is to take the slag, the rocky waste material left over from the SCL process, and sell it as construction aggregate. For making concrete for roads and buildings. If they can create a market for the waste, it improves the overall economics of the refinery. But again, that's another unproven market they have to create from scratch.
And the government has set this commercialization goal for after 2028. That's incredibly soon.
It is an incredibly aggressive timeline. Some would say it borders on the unrealistic. To go from a small-scale technical test on the Chikyu in 2026 to having a fully functioning end-to-end industrial supply chain complete with a brand new refinery by 2028, that would be nothing short of a miracle of industrial planning.
Which, I suppose, brings us full circle. Because if there's one thing Japan is famous for, it's miracles of industrial planning.
True. And that is why this 2026 test is so critical. They're calling it a boundary event. It's the moment where the project has to transition from being a science experiment into a viable industrial prototype.
What are the specific goals for that test?
The main target is to achieve a sustained extraction rate of 350 tons of mud and nodules per day. That's still a tiny fraction of what a commercial mine would need. But if they can hit that number and keep it up, it sends a powerful signal to potential investors and back to the government that the platform is fundamentally viable. It proves the physics works.
So if we try to bring this all together, we have Sato, the strategist, who sees national sovereignty buried in that mud. We have the engineer on the ship seeing a brutal physics puzzle that he's solving with this clever pulp lifting technique. And then we have Tanaka, the factory owner, who sees a potential lifeline for his business, but a lifeline that's currently severed by this giant missing piece of refining infrastructure.
And when you synthesize all those different perspectives, you realize that the Minamitorishima project is more than just a mine. It's a massive, state-funded test case for how nations will have to think in the 21st century. It directly challenges that old assumption that resources are just about endowments, the luck of what you happen to have under your ground.
And it argues instead that resources are about capacity, about what you can build the technology and the national will to go out and get.
It's this grand idea that you can engineer your way out of a geopolitical vulnerability. And Japan is making a monumental bet. They're betting that the incredibly high financial cost of deep-sea extraction is still, in the long run, lower than the potentially infinite cost of losing their industrial independence to a geopolitical rival. They're betting that the security premium is a price worth paying.
It's a massive gamble on every level. They are literally fighting the crushing pressure of the deep ocean on one side and the equally crushing pressure of the global market on the other.
Yeah. In the outcome of this gamble, it won't just determine the future of Japan's high-tech industry, it could set a precedent for the future of how all nations think about securing their survival in an increasingly resource-constrained world.
As the Chinkyu prepares for its next descent, we are left watching a nation attempt to engineer its own geology. They have found the treasure chest at the bottom of the world, and they have built the ship to reach it. But in the race to turn mud into magnets, the hardest part isn't surviving the pressure of the deep ocean. It's surviving the pressure of the global market that waits on the surface.
That's where we'll leave it for this deep dive.